So this video provides some introductory slides and information about the course and about material science in general. So first of all, what is material science? Material science could be defined as the study of the nature, behavior, and use of materials. So these are different in that the nature of the material influences how it would behave, and its behavior would influence how it is used. So materials engineering is related, but slightly different in that it could be defined as designing or engineering the internal structure, meaning perhaps the atomic or molecular level structure of a material to produce intended properties, predetermined properties, properties that we would desire. And material design or materials engineering incorporates materials, mechanics, and management. Materials would be perhaps closer to chemistry, geology, environmental engineering, if you thought of it as what departments deal with. Mechanics would be more related with, more based on physics and math, and management would be more based on perhaps economics. And the major themes of processing structure, properties, and performance are all related with each other, such that one depends on the other, one depends on the previous. So here, performance depends on properties, properties depend on structure, atomic structure, internal structure, and internal structure depends on your processing, which is a part of your design of a material. So you could create with the same material, similar to baking a cake, a different end product because it would have a different structure, and having a different structure would give it different properties, and that would limit or it would define where it could be used for a given material. And a big part of materials is how to select them, and this is what an engineer typically does more than design. So few materials are, so fewer people deal with designing new novel materials, but most engineers often every day have to deal with choosing the right material for a given job. So material properties determine the capabilities of a device, a structure, what have you. In addition, it could influence how it could be made, the technique with which it could be made. So, for example, a civil engineering structure needs to be functional or and safe. So it should do what it is intended to do, and it should do this safely, and it should do this during its service life. The service life could be described as the lifetime of the structure during which the structure needs to do, is able to do what you want it to do. So if the structure stops being functional, that means it cannot adequately perform the task that it needs to perform. So it could maybe perform it partly, but not fully. So this, of course, not only depends on the design, but also on how something is built. So based on labor, and that requires quality control. So it's very complicated concept, a complicated field, perhaps. And another aspect of how structure can be safe and functional during its service life is whether or not it's maintained. So there might be an initial design, an initial building of the structure, whatever it might be, and then in addition, it might require periodic maintenance. So a structure, of course, any engineering structure must also be economical. And here economics is in that it is initially economical, and it includes initial cost, and it includes any future costs such as maintenance costs. So it must be durable. Here durable means that it lasts a long time and is resistant to certain factors that it might be exposed to, such as the weather or such as certain liquids or certain gases that the particular engineering structure is exposed to naturally. And in addition, of course, although it might seem less important, it is pretty important that an engineering structure be aesthetic if it's possible. And of course, more so in the last few decades, it must be environmentally responsible. Again, initially, and here it says maintenance, but it should be initially and later on in its lifetime. So then material selection often requires that you have a trade-off between different properties. So one might imagine wanting both a stretchy and a strong material, or both a strong and a lightweight material for a job. So for the outside of your car, you would want it to be strong, but also lightweight. And you will see that being lightweight and being strong is difficult to have together. So often you will need to sacrifice one property partly to be able to gain in the other property. In terms of cost, the cost of, for example, a residential building, a building that people live in, has maybe 70% of it in the materials used. So this is quite significant when you think about it. The remaining 30% has the money paid to the people designing it and the people actually building it with these materials. So cost is an important issue in material selection. And then operating conditions are important, and they can be different for different engineering structures. So for a building and for an engine, you might imagine that operating conditions are tremendously different. So in an engine, you might have higher temperature exposure than a building. A building might be exposed to, say, from -20 to +50, whereas an engine might be, in certain cases, exposed to, subject to several hundred degrees centigrade temperature. So operating conditions influence what material you can select for a given project. And feasibility determines what is really possible and what is impossible. So as an example of that, I could ask which of these is possible. And I choose this because A, I deal with a lot of concrete in my own research, and B, it's meant to be kind of funny because you don't really think of an airplane, a boat, or a concrete and see examples of these around you. And there is a reason why, when you think about what the properties of concrete are, what the main properties are, and what the needs of a car, boat, or an airplane are, separately from each other, there is a reason why concrete is not preferred over other materials. So this slide shows 3 examples of concrete being used for a boat, a plane, and a car. Although here, I must confess that these are bizarre examples and they're not common examples. So this is the boat, the building of the boat in front of the civil engineering department in the parking lot. You might have noticed this over the years. This is when it was being built in the 1970s. This is an actual plane, a model airplane built out of concrete that was able to take off and land safely. But realize that this is a model airplane, hence it doesn't really have the same, so it would be very difficult at the moment to imagine a full-sized airplane made out of concrete. There, the main problem would be that it would be very heavy. And even if you could get it off the ground, it would be very uneconomical. And then in addition, you would have certain other problems. So for a boat, it would be a little more realistic, because in a boat, much of the weight is being carried by the water. And so being very dense or being very heavy is not an issue. And you might imagine that real common large ships these days are built with steel. And steel is much heavier, or much denser, I should say, than concrete. So then, although a concrete boat seems like it would sink, it wouldn't actually sink. And in the First World War and times around then, there were actually very big warships built out of concrete due to a lack of steel in the Western world. A concrete car, however, would be difficult to have made out of concrete, because the first time you hit anything with your car, you would probably get severe cracking. So then again, with a boat, with an airplane, takeoff and landing would be problematic. You would probably get cracking that eventually grew and failed the system within a few flights. And here too with the car. So for this material, a boat would be the better of the three, the best of the three perhaps uses. But still, if it were so good an idea, you would probably see more examples around it. So then, what we'll learn and what we'll discuss in the course are on this slide as internal structure of materials, as I mentioned, atomic structure and atomic bonds, or bonds between atoms. So there will be a little repetition of first year chemistry, but there will be a new perhaps angle, or maybe we'll try to add a little bit to your existing knowledge of chemical bonding. And then we'll discuss certain properties of materials. Here, a few examples are provided. And we'll also talk about how internal structure influences properties. So the link between structures and properties. And this general discussion would allow you to, at the end of the course, answer these questions. For example, why does a given material tear, but another material, instead of tearing, why does it bend? So similarly, why does a material crack when you try to change its shape and break? And why would another material, say, not crack and break, but it would bend and stay bent? So if you were to take an aluminum foil, a sheet of aluminum foil from the kitchen, and you try to crumple it, you try to push it into a small ball, you would see that it would behave similar to a piece of paper in its behavior, but it wouldn't behave similar to, say, some other material that's, say, for example, a certain type of plastic. So, and if you try to stretch the aluminum foil outwards, trying to make it larger, you'd see that you wouldn't be able to do so, but it would instead tear. But if you had a certain type of plastic, for example, a silicone, thin silicone layer, a thin silicone sheet, you'd be able to stretch this visibly, noticeably, without causing any cracks or tears inside it. And then the answer to why do some materials burn and some other materials don't burn is also linked with the internal structure and the types of bonds they have. So if you were to try to burn aluminum foil, you'd see that it didn't burn, but after a temperature, it melted, whereas a piece of paper would start burning, or a piece of plastic or a piece of silicone would also show some sort of behavior that was different than melting. And so there are lots of these different behavior types, and which depend on properties of the material, which depend on their internal structure, which makes it important to understand what these differences between internal structure of materials may be. And if you're interested, you can go to these, they're not active, but you can copy and paste, or you can rewrite these into YouTube, into an internet browser, and see videos of these different concepts. So to then move on to types of properties. So instead of examples of them, you can classify material properties into various categories. So, for example, mechanical properties are those that define behavior under load. So if you apply a load or a force onto a material, and you look at how the material behaves, for example, when you try to stretch the material under a pulling action, if the material stretches a lot or a little, this is related with its mechanical property. And the mechanical properties are many, because you have to describe what the material does under various different loading scenarios. This may be geometrical scenarios, or this may be differences in the loading applied over time. So a material may behave a certain way when you push on it once, but it may behave a different way when you push on it multiple times in a short amount of time, such as when you try to vibrate the material, when you try to shake the material. Physical properties are different than mechanical properties in that physical properties relate to the way the material is. So it is independent of some sort of outside effect. There is no outside load that changes, that is required to be able to observe the physical property. So density is a classical example. Porosity, or how much moisture the material holds within its structure, as well as shape and surface texture would be examples of physical properties. Whereas mechanical properties would be, say, related with well, an example would be strength, because the strength, as we define formally later on in the course, would be a particular value, a particular threshold above which the material breaks and below which it is intact. So if you try to break a material and you start applying loads or forces from outside in a particular way, when you reach the strength of the material actually breaks, or material does something similar to breaking that allows you to define this threshold as the limit, hence the strength. Then perhaps the chemical properties could be, examples of them could be the composition, for example, the oxide composition, whether you have, say, in a gas, you can think of a gas as, of course, a material. You can have NOx and SOx from environmental engineering examples. The existence of these different oxides would determine whether or not, or say how, for example, this gas would burn. And then you have thermal properties that are related with thermal input. So if you heat the material, if you give it thermal energy, whether or not it relays this energy, relays this heat to a different portion of it relates to its conductivity, or how much it is able to increase its temperature under a given amount of thermal energy would be related with its heat capacity, et cetera, et cetera. So you see that you have a lot of properties. So a course like this one would not discuss all of these properties. And in this particular course, you'll see that we discuss in the second half of the course various different mechanical properties, and perhaps some physical properties, more so than the other ones. And as an example of how to classify materials, you could do this by, for example, state of the material, by intended use, by mechanical behavior types, or by chemical composition and internal structure, or by many, many other ways. So when you try to classify materials, there is no single way of doing this. So according to status simple, you have gas, liquid, solid, but of course you have certain materials that may, in certain parts of their lives, behave as a combination of these. And a semi-solid, which is what you would get when you mix cement powder with water, until it solidifies, it would be a semi-solid. So it would be, in some ways, acting like a solid, and in some other ways, acting like a liquid, hence not being a true member of either category. It would deserve its own category. So then, according to chemical composition, is a common way of categorizing materials. And the common examples of these categories are metals, polymers, ceramics, and some additional categories that you might hear about are, for example, semiconductors, biomaterials, composite materials, or reinforced composites. So metals are those that have metallic bonds from first-year chemistry. And metals can be, within themselves, they can have subcategories of ferrous, meaning iron-bearing, such as iron or its alloy with certain other elements, steel, or non-ferrous, such as aluminum. And then polymers are materials with long chain molecules by definition, and they can be artificial or natural, and natural examples are natural rubber from the rubber tree, certain resins, and for example, wood. So wood and artificial plastics that we use in our everyday lives share many, many properties and show similarities because they are all members of the polymer category. Whereas ceramics that are basically aluminosilicates, indicating that they've got aluminum oxides and silicon oxides in their composition, and they, being a different category, don't behave the way polymers do. For example, a polymer will burn, such as wood, whereas ceramics don't burn, but they suffer differently under high thermal loading. And porcelains or bricks, as an example of clay products, are common ceramics. And you might imagine that metals behave, again, differently than polymers and differently in ceramics. So metals, polymers, and ceramics is a simple, although not complete, a simple way of identifying, of distinguishing between materials. So most every material that you see in your everyday life is going to be a member of one of these groups. If you can put the material in the correct group, then you will be able to, by comparing it with another member of the same group, the same category, you will be able to guess its behavior under a certain condition. So if you can classify something as a polymer, then it is very likely that it's going to not be very resistant to high temperatures. But if you can conversely classify something as a ceramic, an unknown new material, if it is said to have ceramic properties, if it is ceramic by nature, then it will be resistant to high temperatures like a brick would be. So you might say, can my porcelain plate at home resist high temperatures? And the fact that it is a ceramic indicates that it should be able to. Now, composite materials is an additional category because it's, by definition, a combination of different materials. So concrete is an example of this, where you have rocks, you have cement, you have water combined. And here the combination of several materials generally is done intentionally to provide the final material, the composite, better properties than either of the two parent materials. So a combination that gives an improved overall behavior. And certain reinforced composite materials like reinforced concrete, concrete with steel bars inside, or categorizing them. So some materials like concrete and steel and even wood are structural materials intended to carry loads, whereas certain materials like paint or certain insulation materials can be architectural materials, and certain materials can be members of different categories. For example, preservation materials would contain, as a common example, as a common member, paint. And the paint can be an architectural material, and in addition, it could be a preservation material. Now, glass could also be a structural material in certain places, in addition to being architectural. And so here you have the example of wood falling into more than one category, as a load-carrying member, as an architectural member, in some cases, as an aesthetic member, and in some cases, as, say, coating a chipboard. A chipboard is made a board, a layered material, or a board made with wood chips. So then you might have it to preserve whatever is behind the wood in certain cases. So you can have some materials be members of various categories. Now, more importantly, perhaps than the previous ones for this course, is according to classification according to mechanical behavior. Under mechanical behavior, we said that there is an input of load or force, and we look at what the output is, how the material responds. So there are materials that deform and return to their original shapes when you apply and remove a load on them. So if you push on something and you remove this pushing effect, or if you pull on something and you let go, such as a rubber band, it might become longer and it might become shorter after you remove the load. Whereas certain materials, like a plastic bag, would lengthen, would become longer when you apply a force on it. But when you remove the load, it would stay deformed. It would stay in its long, new length. And because of this, you might imagine that a rubber band and a plastic bag must have differences in their internal structures that actually cause this difference. There are some materials that deform in bizarre ways, and common examples are when the material behavior is dependent on temperature or time more significantly than for a lot of common materials. Asphalt, the black material you see on roads, is such an example. So on a hot day, asphalt, being strongly dependent on temperature in its behavior, when exposed to heavy loads, such as the loads from the wheels of an airplane, may actually become soft enough and be indented, particularly because of the high temperature and also because of the time dependence, and because when you park a plane on an asphalt surface, the continued long-term application of this high heavy load in a high temperature situation could cause this. Whereas every day, many thousands of planes go over asphalt surfaces and they provide heavy loads, but they don't provide them when they're moving over a long period of time. So if a plane is moving, it doesn't provide a vertical load at the same point for a long enough time for deformation to happen, significant deformation to happen, as you see here in the image. Or in the winter or in some cool temperature, even if you park your airplane on an asphalt surface, nothing happens. So if something behaves with a strong dependence on temperature or time, then this must be different than another material that doesn't. For example, metals don't really care about time, and they don't really care so much about temperature changes either. So of course, when you heat a metal close to its melting point, it might change its behavior. But when you change the temperature of a metal surface, from say 25 degrees centigrade to 225 degrees centigrade, its behavior doesn't change noticeably. But for asphalt, it does. And because of this, they need to have different ways, different terms to define their mechanical behavior. Another example of this is starch plus water. When you combine starch, nishasta, with water in a certain ratio, it tends to behave strangely. And this is common on the internet as a bizarre material. So when you have, if you were to go to this link or a similar link on the internet, you would see that starch and water combined give you some sort of a paste that maybe looks like pudding. And when you're trying to push this pudding rapidly, when you punch this pudding, or when you try to jump onto this pudding, because the loading rate, because the application of the load is so short or so sudden, hence the loading rate in time is so high, the material behaves like a solid. And if you push slowly, or if you try to not jump onto this starch water mixture, this starch and water suspension, it doesn't, it behaves differently because the loading rate changes. So asphalt on a hot day has a strong temperature dependence and a time dependence, and starch plus water has a strong time dependence in that whether or not you apply the same load slowly or quickly influences the behavior that you are going to observe. Now, what are some modern material needs? Lower environmental impact is one of them that is becoming increasingly important. And of course, trying to get more sophisticated engineering materials, getting better technical properties. So as I said earlier, having low density and high strength combined is difficult, because generally the internal structure that provides high strength does not provide low density. Generally, the denser you are, the stronger you are. And because of this, people now are demanding even lighter, even lower density materials with high enough strength to perform certain jobs. High temperature resistance is another one of these. So as a kind of strange example, I had read that certain automobile companies have been for a long time working on ceramic engines. So instead of a metallic engine, they're working on ceramic engines. But the problem with the ceramic is that your porcelain plate is a ceramic. Hence, when you try to when you drop your plate on the floor, you see that it breaks. Hence, this is a very bad property for an engine. A car engine or a plane engine should not break very easily. But an engine needs to be resistant to high temperatures. And the higher the temperature can be, the better, the more efficient the process generally becomes. So metals and ceramics are suitable in that respect, but a polymer, although it is low density, is not suitable for an engine. So then trying to find novel applications for existing material categories, or trying to improve the technical properties of materials is perhaps an important part of material needs for the future. Now, similarly, environmental impact is of importance. So you could have technical solutions to certain problems, such as we are able to build successful buildings using cement-based concrete and this has been going on for more than 100 years. And technically it's good and we're satisfied, but we know that the environmental impact of cement production is very high. And because of this, now we have been working on trying to develop cements and hence concretes that have lower, say, carbon footprints and lower energy requirements for production. So being able to achieve this requires that we know the properties and know the structure of the materials that we are using presently, so that we can alter these in an intelligent way to be able to achieve our goals. And final words, every engineer, whether you're a mechanical engineer, an environmental engineer, a civil engineer, etc., will have to deal with material problems or a design problem that involves materials at some point. So you will always have the option of choosing the known and easy solution, but there may be cases in which there may be an alternate solution. There may be a solution that is a better solution than what is commonly known and what is recommended to you by, say, your colleagues or your boss. But to be able to choose that, you'll have to know, have some basic understanding of what material properties are linked to what internal factors, internal structure. And an appreciation of material characteristics, the connection between the behavior of materials in its intended design setting and what a material is actually, what an object is made of and how it's produced is important to every engineer. So even if you never create a new material, but you simply choose from a standard set of available materials, you need to be able to choose wisely. And to be able to do that, you need to have at least a basic understanding of what the material is made of, how it is made, etc., to be able to choose the most economical, the most technically suitable, etc., material.